Hi, I'm Laura Reznikoff, and I'm a graphics engineer on Intel's game and multi-core engineering team. And with me for this talk today is Max Rom from the World of Warcraft engine team. We're excited to be able to discuss some of the performance work the team has been doing and introduce to you some of the features and benefits of DirectX 12.
Hi, my name is Max Rom, and I'm a senior software engineer on the World of Warcraft engine team. I've been working at Blizzard for a bit over 5 years, and I've spent pretty much all of that time working on World of Warcraft. Probably the most notable systems I've worked on are the DirectX 12 and Metal graphics backends for World of Warcraft. I'd like to start things off with a little story that was kind of a big aha moment for me in my career. So, for a bit of background, this is a Taldazar. It's a 5-man dungeon that we added for the launch of Battle for Azeroth. And towards the end of the dungeon, there's this staircase that you need to walk up, and it has these void spiders walking down towards you that you're supposed to dodge. And if you don't dodge them, then they explode, dealing damage, and drop a pool of bad stuff. And if you keep standing in that, then you'll take ticking damage. So, one of the first times I was running through this dungeon, I was trying to dodge the spiders, but I messed up and I clipped one. So then I tried to move my character out of the ground effect that I knew to be coming, but I couldn't. My game had completely frozen up, and then a split second later, the hitch was over, but I was dead. At that moment, I realized that the game had locked up compiling shaders. So, after dying to a system I maintain, I was really motivated to fix it. The root cause of the issue is that in a DX11 style world, you're only really describing to DX11 what you want drawn right then and there. The driver has threads that try their best to hide the cost of doing stuff like just in time compiling shaders and whatnot. But in DX12, there is no driver thread to fix things up. So if you just in time compile shaders, then you're just going to hitch the game. So the very next day, I started working on trying to solve this problem. I started coding up an async pipeline creation system. And I realized that there's uh, some beauty to this, to coding up a system like this, because then the application has full control to just simply not draw an effect until it's ready. And by doing it that way, then we can guarantee that the game is hitch free. Because in a DX11 world, we were just kind of describing the scene to DX11 and hoping that the driver can pull everything together in time to not hitch. But in DX12, we can just defer drawing an effect, which is in a lot of cases completely unnoticeable to the user, and we create a completely hitch-free gameplay experience. DirectX 12 style APIs offer a lot more control to the application, and we've seen some pretty big wins from leveraging them. So probably the biggest win we got as far as frame rate improvements was multi-thread commandless generation. This was a big win over doing something like a driver replay thread. By having coarse chunks of rendering work broken up onto a thread, like we initially started with moving our shadows onto a thread by itself, and then other chunks, logical chunks of graphics work being put onto threads. The mixture of application code and API calls in parallel with each other allowed us to start leveraging a lot more of the CPU. And it ended up being large frame rate improvements. I think when I initially got shadows rendering on a thread, that was a 10% frame rate improvement right off the bat. So it's incredibly powerful to start leveraging commandless generation in a truly parallel way. Uh, and then, as I talked about in the story, the asynchronous pipeline creation was really large for us. In edge cases, we would have pretty bad hitching. On top of the texture creation, we also furthered that idea to texture uploads, so creating and uploading images off disk. We leveraged the DX12 copy queue API, and we're able to get those asynchronously connected, and then we could synchronize on the GPU uh, when they were ready. So the asynchronous pipeline creation and the texture uploads pretty much solved all of the hitching issues that World of Warcraft had, from a graphics rendering perspective at least. WoW has had a history of needing a warm up period. Like when you first log into a world, that first turn could be pretty choppy. But now with DX12 and all of these features that we're leveraging, we can pretty much load in, spin the camera, and it's pretty buttery smooth. So that's really nice. So when Balfour Azeroth initially shipped, we had a DX12 backend in, but it was still sort of in a beta phase. We didn't default users onto it. It had feature parity with DX11, but it wasn't really accomplishing anything that DX11 wasn't already doing. And then over the course of the minor patches throughout the expansion, we started bringing in the multi-thread command list generation, async pipeline, texture creation, and leveraging these more powerful application control features. So, looking back at client performance before and after all of our changes, if we look at a specific expensive scene, without all of the changes, we're pulling about 50 FPS. And then after the changes, then we're pulling about 80 FPS. So the multi-threaded command list generation specifically really sped things up for us. It's also worth noting that getting the work broken up into threads was a huge amount of work of several engineers to do. And after we finally got it working in DX12, we then went back and experimented and got DX11 deferred command lists working. DX11 does have a command list generation API, and we weren't leveraging it up to that point. At least for us, it wasn't until we were really forced into the DX12 model that we were able to really feel like we should invest the time to convert all of our existing code. But once we got the DX11 deferred command lists in, we were able to get DX11 to match that 80 FPS, which was really cool because DX11 is supported on older hardware. But the thing you can't do with DX11 is the asynchronous pipeline creation. So I think one of the big wins for DX12 is really the control over when objects are created and really allowing the application to solve hitching issues. So then looking forward, a DirectX 12 feature that is in the upcoming Windows release that we're really excited about is variable rate shading.
Variable rate shading is a feature that has been added to DirectX 12 to help developers selectively reduce pixel shader work. Rather than shading per pixel, VRS allows you to specify a shading rate for an entire group of pixels. And this allows you to change the number of pixel shader invocations for the group. Max will be showing us a clear visualization of this a little bit later. Another way of thinking of this is it's like an extension to MSAA. It's like you're having an LOD control over your shading rate. VRS is controlled in different levels depending on the VRS tier you choose. Tier 1 VRS, which is what is currently supported by Intel's Gen 11 Ice Lake products, allows setting of your shading rate per draw call. Tier 2 support adds the ability to control your shading rate by screen space mask or from your vertex and geometry shaders. For the broadest current hardware support, this talk will focus on the usage of Tier 1 VRS.
Let's do a little demonstration of VRS in action. Here we're looking at an apple. We're just zoomed in to the 4x4 pixel intersection of the apple with the sky. See here, the reddish part is the apple, and that bluish part is the sky background. So if we look here, the left-hand side is the traditional rendering with 1 pixel shader invocation per pixel on both the sky and the apple. But on the right, The sky is still being run through traditional 1x1 VRS off, but the apple is being run in VRS 2x1 mode, which means that the pixel shader is being run once per set of 2 pixels, and the pixel shader is being run at the midpoint between those 2 pixels, and then the results are split across 2 pixels, as if the pixel were that rectangular 2x1 shape. And then here on the right is VRS 2x2. In this case, the pixel shader is being run once per 4 pixels, and then we're getting even more averaging of the colors. So now let's just focus on the VRS 2x2. The interesting thing here that you'll notice is that the aliased edge of the apple has been preserved this whole time. We still have the sky jutting in to make those L-shaped pixels. So even though we're running the pixel shader on the group of 4, the vertex shader is still only applying it to the pixels that intersect. So we preserve edges with VRS. And then on the right, we have 50% render scale, which is a somewhat similar effect, but you can see clearly when we render at half resolution, we lose that fine edge and the image becomes much more aliased, but we're getting conceptually the same pixel shading. So now that we're all on the same page about what VRS is, the next question is, how can you apply VRS in video games? So generally the goal of applying VRS is to make an effect that is almost or completely unnoticeable to the user that VRS is being applied. Then you can save pixel shader cost without changing the way the image looks hardly at all. So if you consider this image right here in World of Warcraft, you might be wondering which systems would be good candidates to run VRS on. And actually, interestingly enough, this image has VRS applied to all the systems that we found had big wins from running VRS. And which systems those are is actually fairly counterintuitive. So here highlighted in red is all the systems that had VRS running in the previous image. It's essentially terrain, buildings, and distant terrain, surprisingly. We'll go over all these systems in detail, but for now it's interesting to note that it's basically not running VRS on the fine detail models and characters, but everything that's fairly static is a good candidate. So probably one of the first things that comes to mind when considering VRS is what about distant things, things that don't need as much detail? If it's far away, we can probably get away with not drawing as much detail into those parts of the scene. So let's go ahead and zoom in on this window right here on the top part of this building that's kind of in the medium distance part of the scene. So right here we're looking at the window zoomed in with no VRS applied. I want you to take note of how the fine details of the glass look and then the wood paneling below it. So now I'm going to turn to VRS 2x1 and you can see that the fine details of the window are blurred a little bit and the paneling work stays about the same. And now we're going to switch to 2x2 and you can see that the glass work is blurred a little bit more and the woodwork is still about the same. And the 2x2 is the same as the image is in the larger picture. So if you look on the left-hand part of the screen and see this circled window, you can see how losing some image quality on the detail work of this window is not contributing to the scene very much from where the player is standing. So then if we go back and compare the window with and without VRS, the really interesting thing to notice is the silhouette of the building against the sky. If you compare those two silhouettes, they're identical, even though all of this building was being run with VRS 2x2. And this is the part that really sells the VRS as being largely unnoticeable. You don't really notice the fact that that window detailing is blurred a bit, but you would notice if the silhouette of the building became a lot more aliased. But that's not happening here with VRS. Preserving the silhouettes is one of the big reasons why applying VRS on things at medium and long distances away from the player can be almost completely unnoticeable, because at that distance, the silhouette is the most important part of the image. So if you recall back to the red image, it wasn't just distant objects that we were applying VRS to, we were also applying VRS to the terrain really close to the camera. So now we can take a look at how VRS applies to systems like terrain. If we look at this image right here, the scene is almost entirely terrain, including terrain directly in the center of the player's area of interest, and even closer, directly in front of the camera. So if we switch this scene into wireframe, you can see these large triangles next to the camera. And this is the interesting thing. In the first example we looked at, we were looking at things at medium and long distance that weren't that important. And in that scenario, silhouette preserving was important and losing image quality was not that important. But in this scene, it's a very different reason why VRS can be a big win. Here, there's no silhouette to preserve, but if you think about what's happening here, you're applying a texture of a specific resolution to a triangle that's relatively large in screen space. And what's happening here is actually the texture we're applying for the terrain doesn't have enough detail to fully saturate that screen space triangle. So if we reduce the pixel shading rate of it, we're actually more closely matching the texture resolution that we're using. So then if we look at the same scene with the terrain being run at VRS rate 2x2, the terrain looks about the same as it did. So here we can zoom in side by side, and on the left we have no VRS, on the right we have VRS applied, and if you look especially around the character, that terrain texture that's rendered looks almost exactly the same. You wouldn't notice that you were running at a half pixel shading rate unless you had the A-B comparison right in front of you. And then if we highlight the medium distance terrain, it becomes more noticeable that we are losing some image quality with VRS. The right image, the terrain looks a little bit blurrier, but at that distance, it's a lot less important and less noticeable that we're losing a little bit of image quality there. So when we're talking about performance speedups from running VRS, remember it's reducing the pixel shading rate. So systems like terrain, especially in a scene like this where it's almost entirely terrain, you can get reduced pixel shader cost on almost all of the scene. So running it on systems like terrain can be a very large performance speed up relative to anything else you could do with VRS, and the effect can be largely unnoticeable depending on the texture resolution that you're using for terrain and whatnot. So for World of Warcraft, we're looking to use VRS on the aforementioned systems dynamically based on if we're GPU bound and failing to meet FPS targets. And we've come up with this interesting trick to more smoothly turn VRS on and off in front of the player without them noticing. So a phenomenon that we've noticed is that while playing the game, if you go from the VRS rate of 1x1 to 2x1, that's a far less noticeable jump than going from 1x1 to 2x2. And a lot of the reason for that is because people are playing on monitors with a 16:9 aspect ratio, which is pretty close to 2x1. So you leverage the aspect ratio of the monitor to create a smoother transition. So you can go from VRS 1x1 to 2x1 to 2x2, and it's a lot smoother transition with a lot less popping in front of the player.
One topic I'd like to revisit, because we've received a lot of questions and comparisons on, is the comparison between variable rate shading and using render scale. So some of the pros of VRS is that it preserves your edges and silhouettes. This is really one of the biggest benefits. This means that it works well with edge-based AAA, such as CMAA, and it also gives you a lot of bang for your buck on retaining the fidelity of the edges of your models. So this reduction in quality is far less noticeable. It also gives you finer grained control over which systems have VRS applied. This can be important for systems like text, where you're trying to use a depth based effect and you want to still have things be crisp. Another benefit is that VRS has no upscale pass requirement. If we then look at the pros of render scale, you'll see that this also reduces your vertex and bandwidth costs. So using render scale is much more like the comparison of using a hammer versus we like to consider VRS more like a scalpel. So you'll see larger performance improvements by using render scale because it's going across the full breadth of your work. Also, with render scale, you'll see a smoother range of intensity, i.e., all the values between 1920 to 3840. So, ultimately, when comparing VRS with render scale, you want to make sure you choose the right tool for the job. For large performance wins, where you can take a reduction in quality across your entire scene, you'll probably want to investigate render scale. But if you want to just get smaller performance gains and have fine grained control of where you're losing visual quality, VRS can be a very valuable tool.
So now let's talk about some of the limitations of VRS, some things that we tried that didn't work very well. If we remember earlier in the image of what was red in VRS, things that weren't red were fine detail, models, and players, things with very high triangle density. You both get poor VRS speed up from it, and it hurts the image quality fairly noticeably. So there's not much motivation to run VRS on anything with high triangle density, both from a correctness and a performance speed up perspective. Another system that we were hopeful VRS might be able to be a good candidate for is particle systems. So if we zoom in to this player's feet, we can see the particle effects of a spell that the character's casting. And unfortunately, VRS on these alpha tested particles just makes them look very noticeably blocky. You look at those white specks, they're noticeably pixelated, especially the pixelation of the edges of the effect. There are potential speed ups from running VRS on systems like this, especially if you have a lot of them on screen, but at least in World of Warcraft's case, the noticeable pixelation didn't really create a good looking effect. So overall, we were very happy with running VRS on systems that have relatively low triangle density, such as terrain and buildings, and things in the medium to long distance can heavily benefit from it because they preserve silhouettes.
To sum up, the best places we found to leverage variable rate shading in World of Warcraft also proved to align with other best practices we've seen in other titles. In short, your heavy pixel shaders in areas where lower quality may not be perceptually noticeable to your players are generally good candidates to use VRS. Some possible areas we've explored include terrain, areas under motion blur or depth of field effects, and objects in your distance. To give you a rough idea of the performance gains we were seeing with our use cases for variable rate shading in World of Warcraft, we took a look in particular on terrain in an Elwyn Forest example. So with VRS set to 1:1, so basically not taking advantage of variable rate shading at all, we were seeing about 61 frames per second. If we switch the terrain over to 2:2, we saw a gain of about 7 frames per second. And with it set to 4:4, we were seeing about 76 frames per second. So this was a pretty good gain for us with variable rate shading on the terrain system. And it was pretty consistent with what we've seen in other usages of variable rate shading. So when you're balancing visual quality with variable rate shading, we've seen about 5 to 10% gains to be pretty common in a deferred renderer. We've seen that you can usually get a bit more performance out of forward renderers, so you'll have to adjust that for your particular engine. One way you can evaluate the performance benefit and visual quality of using VRS in your engine is by changing your shading rate in Intel's Graphics Performance Analyzer. You can do this before even integrating VRS into your own engine. So here I've selected a terrain region, and with the state selected, I can find the shading rate and a drop down. And then at the top here, you'll see we have our current FPS. If I go to the drop down, we can change our shading rate, here 4x4, and you'll see everything recalculates. Once that's done, you'll see our updated FPS, so here 72. If I select our output of our scene and change it to object, you can actually see here the visual effects of your VRS shading rate selection. I hope this has let you see just how quick and easy it is to evaluate both the performance and the visual quality of applying variable rate shading to your systems in Intel's Graphics Performance Analyzer. Again, I just want to emphasize that you can do this even before integrating VRS into your game engine. So before you make the investment, you can quickly evaluate the trade-offs. From this talk, we hope you've seen the value and the power of some of the newer DirectX 12 APIs. In particular, we went into depth on variable rate shading and how it can be a valuable tool for selectively getting performance gains while retaining visual quality. We've seen how per draw call VRS or tier 1 is very easy to integrate if you already have a pre-existing DirectX 12 engine. And it can be dynamically turned on pretty seamlessly. We've also shown you some of the best use cases for variable rate shading and how you can use it to reduce pixel shading costs with minimal reduction in your visual quality. Additionally, we've shown you how to use GPA to quickly get estimates and also test the performance and visual quality of changing your shading rates. And we've also presented some rough estimates of the performance gains we're seeing on Intel's Ice Lake hardware.